Okay, we're going to try to finally get around to probability in section 13.3, and let's get some vocab out of the way first. Alright, first thing we need to know. When I say sample space, that means it's a set of all possible outcomes. So what I have here is two kind of simple ideas. If you're tossing a coin, the sample space would be heads or tails. If you're tossing a dice or die, the sample space would be 1 through 6. Okay, if I say the event, if S is a sample space, then the event is any subset of that sample space. Usually what we talk about is the event being what you want to happen. So the event is what I want to happen, versus when I talk about probability, it would be, if you look at this little formula here, the number of elements in E, meaning the number of elements in what you want to happen, over the number of total elements in S. Okay, so let's do a really easy example. If I said, what's the probability? We're going to roll a die one time. What's the probability of rolling a 3? We would say, okay, well, there's 1 3 on the die out of 6 total choices, so that would be the probability of rolling a 3. Okay, what if I said, what's the probability of rolling an even? Okay, so if we did that, we'd say there are 3 evens on there out of 6 total, so it would be a 1/2, 1 to 2 probability. Now, just so you know, sometimes the book will give it in fractions, sometimes they'll write it as percent, so this one that we just did, we could say there's 50% probability. So just kind of get used to seeing both notations. Okay, my next example is just to show you that sometimes it's easier to list out everything in the sample space. And it does take a little bit of time, but it's kind of quick when you're asked some questions, maybe like an A through F about tossing a coin or something like that. So what I've done here, you don't have this on your page, so you might want to press pause, take a second, and at least jot out the first few. But what's going on here is I'm flipping a coin 3 times. So I have first toss, second toss, third toss kind of listed out with all the possibilities. And then what I have over here are all the possible outcomes. So I could have 3 heads in a row, I could have 2 heads then a tail, a head then a tail then a head. You know, I have 8 different possibilities. So I listed them out down here. Now what you might want to do is leave the screen here but flip your packet to the next part, because there are 2 questions on the back side, and you'll see how easy it is if you take the time to list it out. So the first question on the back side says, what's the probability of getting exactly 2 heads? So if I'm looking at all my choices and I'm looking for exactly 2, there's one that has exactly 2, there's another one with exactly 2, another one with exactly 2. So what I see is, for exactly 2 heads, I would say there's 3 out of 8 total possibilities for exactly 2 heads. Okay, now, the second part says, what's the probability of getting at least 1 head? So 1 or more. So if you're looking at all these, I can kind of keep checking now, right? So 1 or more heads, 1 or more heads, 1 or more heads. There's only one at the bottom that has no heads in it. So I would say, to be at least 1 head, you could say 7 out of 8 possibilities. So let's tackle a little bit of a harder one. Look at example 2. 7-card poker hand is drawn from a standard card of 52. What's the probability that all 7 cards are hearts? So this is one where you probably wouldn't want to list out that entire sample space of possibilities. So we're going to go to kind of our combinations, permutations idea. Okay, so let's think about it. If I want to know how many elements in the entire set, okay, so I'm going to use the same notation from the front of this page, in the entire set. Alright, so we're going to be talking about a combination, because once again, it doesn't matter what order I choose my 7 cards, I still have the same 7-card hand. Alright, so if I do a combination, 52 cards, choose 7, I get this 133,784,560 for the number of parts of my set. Now, if I only want to focus on the probability of 7 cards all being hearts, I want to talk about just the hearts. So, if there are 13 hearts in the deck, the number of elements in what I want to happen is they're all hearts, would be, once again, a combination, doesn't matter what order, of 13 hearts, and I want to choose 7. Okay? So the total for the elements of what I want to happen would be 1,116. And then remember from the front of this, the probability of an event happening is a number of elements in the set that I want to happen over the total number in the entire set. So I'm going to take my 1,716, put it over this big number I got, and again, all calculator work. All right, but you do need to show me a couple steps on these. And then if I do it, scientific notation is just fine. 1.28 times 10 to the negative 5. It's a really small chance of all that happening. So let's do another similar one, and maybe I won't write out every single step this time. Example 3. 2 cards chosen from a standard 52 cards. What's the probability they're both queens? Okay, so if I want to know the probability of this event happening, I want to do the probability of only queens over the entire set. So on the top, I'm going to have a combination, 4 queens in the deck. I want to choose 2 of those 4. Over the entire 52 card deck, choose 2 of them. Okay, so if you want to crank all that out in the calculator, we're down to, here's my decimal form. Okay, so again, pretty small possibility of that happening, probability of that happening. The next thing we're going to talk about is a little more vocab. Mutually exclusive events. This means 2 events that have no outcome in common are said to be mutually exclusive. So here's kind of a silly example. If I say that set E is the fact that the animal is a dog, and set F is the animal is a cat, I would say those are mutually exclusive because you can't be a dog and a cat at the same time. And we're not talking about any of those silly cartoons where you have cat dogs and all that kind of stuff. So, dog and cat, mutually exclusive. Okay, so let's take a look at the next page now. So if we decide that 2 events are mutually exclusive, we want to know the probability that one or the other occurs. We're going to look at the union of the 2 probabilities of the events. So just for some kind of notation here, if I have the union of 2 events happening, I'm going to add the things together. So or for us right now means addition. When we talk about and later, we'll be talking about multiplication. So I want the probability of E union probability of F. So this is if they are mutually exclusive. So take a look at example 4. Card is drawn. What's the probability that is a 3 or a face card? So we have to make sure we understand. If it's a 3, it can't be a face card, and vice versa. If it's a face card, it can't be a 3. So if I want to know the probability of this happening, we're going to look at the probability that's a 3 plus the probability that's an F. Okay, so let's do some simple probability. There are 4 3s in the deck, over 52 total cards. This is an OR statement, so it's going to be addition. And there are 12 face cards in the deck over a 52. Okay, add those up. And then always, we're going to reduce these, so I'm going to get 4/13 for probability. So again, they are mutually exclusive. Now, if they're not mutually exclusive, meaning there's some overlap in their parts, we're going to treat it a little bit differently. We're still going to tackle it as an OR statement. We're going to add it together. But then what we have to do is we have to subtract out the probability of when the 2 events have that overlap. So you see the little upside down, this guy? That's the intersection of the 2 sets. So let's look at a concrete example. If I have a face card and a card that's a spade, you do have to notice, okay, there are some face cards that are spades, so there's an overlap of the events. So the way to write it out, if you want to kind of do it little by little, probability that's a face card, that would be 12 face cards out of 52 cards. Probability that it's a spade, you have 13 spades in the deck out of 52 cards. Then you have to ask for the overlap. How many face cards are spades? There are 3 face cards, Jack, King, Queen, that are spades. So that's 3 out of 52. Okay, so then if I follow the formula, I do the OR part of the statement first. So face card plus spade. And then I subtract out the intersection, the face cards that are spades. Okay, and if I do all that, I get 22 out of 52. And then once again, reduce, 11 out of 26. So those are when they are not mutually exclusive. So another case we're going to talk about is the intersection of independent events. Okay, an independent event is something where one event does not affect the probability of another. So my example here is the probability of showing heads on one toss of a coin doesn't really affect the probability of the second toss. Now you could kind of argue that point, but in reality it doesn't really affect it. So if we want to look at the intersection of events, an AND statement in other words, we want to look at the probability of E times the probability of F. Okay, so let's look at example 6 here. Jar contains 5 red balls and 4 black ones. A ball is drawn at random from the jar, and then it's replaced back in, so it's not going to affect the next pull of the ball out of the jar. Then another ball is picked. What's the probability that one is red and the other black? Okay, so this is an AND statement because you're putting it back in, and they don't affect each other. So the first one, red, 5 out of 9 total. It's an intersection of events, so multiplication, 4 out of 9 for the black. So we're getting 20 out of 81. Okay. All right, the last concept we're going to talk about here is the complement of event. So kind of like complementary angles in geometry, where 2 angles together are 90. Here we're going to say 2 complements for probability are going to equal 100%, or 1 total. So if I want to talk about the complement of an event, it's the set of outcomes, by definition, in a sample space that are not what you want to happen. In other words, what you don't want to happen. Okay? And so to find the probability of E prime, the prime we're going to say is the complement, we take 100%, 1 total, minus the probability in E. And this comes in really, really handy when you're trying to do those at least questions. At least one of these, at least 2 of these. Okay, so it's much easier to find the probability of something not happening and then subtract it from a full 100%. Okay, so let's look at an example. We'll look at 2 of them. Example 7. Jar contains 10 red and 15 green. 6 balls are drawn at random. What's the probability of at least 1 ball being red? So, what I want to happen is at least 1 ball is red. So then you think about the complement of it. The complement would be there are no red balls in this urn that I pull out. Okay, so it's kind of tricky. Or in other words, you could also say all green, maybe. Maybe another way to think about it. Okay, so if I want to know the number of elements in E prime, the complement of E, meaning all green, we would say it's a combination of 15 total green balls, choosing all 6. Okay, so that would be C of n prime. Now, the number of elements in the entire set for the bottom of our fraction would be a combination, 25 total balls, choose 6. So then, the probability of E prime, so what I don't want to happen, would be this combination, 15 choose 6, over the combination, 25 choose 6. All right, crank that out in the calculator. That's kind of a big number here. Actually, a small number if you think about it this way. 13 out of 460. So that's what I don't want to happen. So if I want to figure out what I actually want to happen, it's going to be that 100%, or 1, I'm not going to write 100, minus what I don't want to happen. And here's what I end up with, a 0.97, in other words, 97% chance of having at least 1 red ball. Pretty good odds there. This last example is pretty tricky, so I anticipate talking about this one again in class tomorrow. So here's what it says. Probability in class of 35 students. What is the probability that at least 2 have the same birthday? Okay, whenever you see that at least, it's kind of tricky. So here we go. Let's say E prime is that no 2 people have the same birthday. So when I'm figuring that out, I want to figure out, okay, now this is tricky, because the order matters, right, on this one? And I'm choosing dates. Okay, so I have 365 days to choose from. I'm choosing 35 of them. Okay, so I get this 8.89 times 10 to the, oh boy, is that right? 88. It's crazy. Small, 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 right? And then if I want to know what's the probability of that happening, I'm going to take that number over, okay, here's what we might want to talk about tomorrow. It's kind of tricky. 365, because if I listed it out under each of those 35 spots, to the 35th. Okay, so it's going to be kind of a crazy number here. All right, so then what I'm going to do is I'm going to do 100% minus that crazy number that our calculator is going to tell me, and here's what I get. A 0.814, or 81% chance that at least two have the same birthday. That's actually a pretty high probability.